Next topic is the third law of thermodynamics. It is also common as we have already discussed this thing in the graduation level. Okay, so let's start without killing so much more times. So from the Nonstreet theorem, we know that we have already just finished this thing. So limit t tends to 0, del Cp equal to 0. Okay, that is the heat capacity of all substance at absolute 0 of temperature must be same, because if they are not same, then delta Cp means the change of the heat capacity will not be 0. Okay, hence at low temperature del Cp by T is 0, because as Cp is 0, then del Cp by T Cp by T is also 0, or a finite quantity, because as Cp is not 0 at that condition, then Cp by T gives a finite quantity. The entropy change due to the lowering of temperature is given by, we know that the entropy change del S equal ds equal to dq by T, and if you replace this thing, dq equal to Cp dt. Okay, and how can you get this? Because it is coming from the second law of thermodynamics. Dq equal to actually dq by dt at constant p means heat change at constant pressure equal to Cp. So if you manipulate this thing, I can just make this thing easy. We know that Cp equal to dq by dt at constant pressure. So dq equal to Cp into dt. So I have just used this thing. So in place of dq, I can write Cp into dt by T. So if I integrate this equation from the temperature limit of 0 to T, then 0 to 2 ds equal to 0 to T Cp dt by T, and this simply gives you S, and if you put the limit value, then St minus S0 equal to 0 to T Cp by T into dt. So since Cp by T is a finite quantity, means either 0 or some finite positive quantity, so we can say that St minus S0 must be a positive quantity. Means if Cp by T gives a finite quantity not 0, then St and S0 are not same. That means St means the absolute entropy at some finite temperature must be greater than its absolute 0 entropy value. Must be positive quantity, that is St greater than S0. In other words, the entropy change of any substance at any temperature must be greater than its entropy at absolute 0 of temperature. So this is the statement of this above equations. So in 1912, Planck proposed that the third law in this form: the entropy of a solid or liquid, that means condensed system, is 0 at the absolute 0 of temperature. So from the Nonstreet theorem, we know that limit t tends to 0 delta S equal to 0, that we have already discussed in the previous section. And from the Planck's law, Planck has proposed that when limit t tends to 0, then S also equal to 0, not the delta S, means not the change in entropy, the absolute entropy also 0. Okay. So at 0 Kelvin, the solid reactant and solid product have 0 entropy. Hence the entropy change is also 0, because delta S means product entropy minus reactant entropy, and if individually they are 0, then their change is also 0. It can be shown from the statistical consideration that entropy becomes least when the substance present in a perfectly arranged crystalline state. Okay, it's true. We'll definitely prove this thing in the later section. Thus, Planck's theory is true for pure and perfectly crystalline substance. The third law therefore states that every system has a finite positive entropy, but at absolute 0 of temperature, for a pure and perfectly crystalline substance, the entropy becomes 0. Okay, and this definition is given by Lewis and Randall. So this is the statement of the third law: for a pure and perfectly crystalline substance, the absolute entropy is 0 at absolute 0 of temperature.